Hello, everybody. Thanks for joining me today. We're going to start into Chapter 7, Section 1 today. And what's Chapter 7 mainly deals with are various properties that we use in algebra to simplify algebraic expressions. And this particular section, we're going to work on simplifying expressions using the properties of exponents. So the first thing I need to show you or discuss is what a monomial term is. Now, a monomial term in an algebraic expression is a part of a polynomial where you can have constants and you can also have variables, but the constants and the variables have to either be separated by multiplication or addition. If there are multiple things in the polynomial that you have and they are separated by a plus or a minus, that will actually constitute more than a monomial. Monomial means one, which is a single term. If things are separated by pluses or minuses, it means they're more than one term. So, as an example, if you look here, you can see that on the left, we have all of these expressions that you see are examples of monomial terms. If you just start with the number 3, that is just a constant, but that is a monomial term because there's one thing there. Now, this is where it does get a little confusing. If you look at this right here, we have a 5x. That 5x is still considered a monomial because the two things that we have there, the constant and the variable, are separated by multiplication. Now, looking over this list, another example of a monomial would be this 4 right here. So you can see we have 4, a, b, c to the third, d squared, and e. All of those letters, and then the number 2 and the powers, because they're separated by multiplication, that is fine. That is a monomial. Now, same with this 10t to the third, same with this negative 24x squared y to the sixth. Those are all monomials, as well as what you see right here, where we have an a squared and a b, and it's being divided by 2. Now, you might look at that and say, well, wait a second, that looks really close to this. And it does, but there is a difference between those two. So when you have a term where you have your variables and they are being divided by a number, that is perfectly fine. That is still a monomial. But if you have variables and it's being divided by another variable, that is not a monomial. So then you would say that to be no. So on the right, you can see there's examples of no. We have f minus 4 because the f and the 24, I meant to say not 4, f and 24 are separated by a subtraction sign. That actually constitutes two separate terms. So that would be called a binomial. But that is not a monomial. Neither is negative x plus 3 because there again, it's separated by a plus. So that is a binomial. Same thing with this one. If there's a plus or minus in between them, it is not going to be a monomial. Also, if you are dividing by a variable, it is not going to be a monomial. So let's move on and we're going to practice. We're going to take a look at these. We're going to quantify these as a monomial or not. So what I'm going to do is I'm going to highlight the ones that are monomials with light blue. So I'm going to put the yes ones, okay? And we will highlight the ones that are yes with blue. So if I'm looking at that first one, n minus 14, that one is separated by a minus. So as I said, if there's a minus in there, it's going to be no. So I'm going to make that one red. So that one is no. Looking at the next one, 4h minus 12i. Once again, there's a minus sign in there. So that's going to be a no. And actually, I'm going to go through in all of these ones that have a plus or minus on them. I'm going to go ahead and highlight in blue. That's not a monomial. This is not a monomial. So there's all the ones that have pluses or minuses in them where there's numbers or variables being separated. So now we're going to go by the next one. And if we look at the f squared times g divided by 3, so that one has variables on the top, but it just has a single number on the bottom. So because it has a single number on the bottom and not a variable, this is going to be yes. Now, in a similar fashion, we have, I'm going to skip a couple, but we have this one right here. If you look at that one, that says kj squared, but we're dividing by y. So because we're dividing by a variable and not a number, this one would be no. So now I'm going to jump back up to the 4r to the third st squared. Those are all numbers and letters, but they're just separated by multiplication. So we can go ahead and highlight that with a blue because that is yes. The same goes for the negative 27a squared b to the fifth. That is just all separated by multiplication. So you can quantify that as yes. The number negative 9, that is definitely a monomial because there's only one thing there. And 8d, it's separated by multiplication, so that would also be a yes. That is a monomial. So there's a little activity just to kind of show you how to recognize monomials and things that are not monomials. Really, to me, the only tricky one in there is going to be these where you're dividing. If you're dividing by a variable, it's a no. But if you're dividing by a number, it's a yes, as long as the numerator just has multiplication in it, which both of those do. So now the next thing I need to show you are some rules of exponents. So what do we do to be able to simplify various algebraic expressions? Well, there's three different rules that we're going to talk about today. And the first one is called the product property. And so what it allows you to do is if you have a number, a base number to a power, and then the same base number to another power, what they allow you to do is just write the base number once and add up the exponents. So as an example of that, if I had, I don't know, x to the third power times x to the fifth power, the key thing here is that the bases are the same. They're both x's. So what I'm allowed to do is rewrite that as x and then to the 3 plus 5, which is x to the 8th power. And you can only combine the exponents if the base is the same. That's very important. Now, the next one is called a power, and I like to call these power to a power because it's exactly what you have. You have this base number to a power, and then all of it is being taken to another power. So I call that a power to a power. When you have a power to a power, you are allowed to just multiply the two exponents together. So as an example of that, if I had x to the third power and then to the seventh power, like that, you would rewrite that as x to the 3 times 7, which is x to the 21st power. Now, you don't need to show this step here and this step here if you don't want to. I'm just doing it so you can see how the exponents are combined. But when you have a power to a power, the exponents multiply. Now, the last one is called the power of a product. And what that allows us to do is if you have two things inside a set of parentheses that are multiplying, and then on the outside there's a power, it allows that power to go on both of the things that are inside the set of parentheses. Now, I got to warn you with this one. This one is mixed up all the time by math students, all the time. I see it constantly with even my Algebra 3 students because what you have to notice is the A and the B on the inside are multiplying each other. And this holds true for multiplication and division, as you'll see in a second, but only multiplication and division. If we had something that said A plus B to the second power, for instance, you cannot do this formula because of the plus. Okay, the only time you could do this formula is if it's multiplication or division. So as an example here, if I had xy, the quantity squared, that would be the same as having x squared y squared. So now there are three different rules of exponents that we are going to use to do some simplifying algebraic expressions. And I have four problems I'm going to show you today. So the first thing you see is we have t to the third times t to the fourth. So the expressions themselves are multiplying each other. And so what we do with that is we write the base one time, and then we take the powers and we add them up. So it becomes t to the 3 plus 4, which becomes t to the seventh power, just like that. Now, the next one is a little more complicated because there are numbers and letters and exponents. So, what it might be helpful to do for this particular one is to reorder the things so we can see how they're going to simplify. The reason why we're allowed to reorder is they all are separated by multiplication, and multiplication is commutative, which means we can move terms around and not affect the final answer or what the expression represents. So I'm going to go ahead and move this around. So I'm going to write 3 times 9. I'm going to put the two constants together. Then I'm going to write q to the second and then q to the fourth. Now we can go ahead and combine different things. So we have 3 times 9 first, which it becomes 27. And then the q's, because the bases are the same, we could go ahead and add their powers. And again, you don't have to write this step. I'm showing you what happens there, but it becomes 27q to the sixth power, just like that. Now, the next one is even more complicated because there's a bunch of parentheses, but in reality, it's really not. It just looks more complicated. The parentheses, they're only separating, if you notice, the reason why they put parentheses here is because of this -3. They didn't want you to think that it meant -3. So they had to put parentheses around it. But it's all multiplication all the way across. So once again, we can apply the commutative property to reorder things. So I'm going to do that. 5 times -3. Then I'm going to write my u's, u to the fourth, and then u to the fifth, and then v to the first. I know there's nothing there, but it is v to the first, and then v to the third. So what I did is I reordered everything so all the like terms are together so it's easy for us to see what is going to get combined. So 5 times -3 is -15. And then I have u to the fifth, or sorry, u to the fourth and u to the fifth. The powers here are going to add. So it's going to become u to the ninth power. And then the v's are going to go ahead and add up as well. So 1 plus 3 becomes 4. Now, it's really important to remember, if you have a variable like this where there is no power on it, there is a power, they're just not writing it. It is to the first power. I like to write it so when you are combining the variables, you don't forget to include it when you combine things. So you can see our final answer then would be -15 u to the ninth v to the 12th. Now, the last one we're going to do today looks even more complicated, but it really isn't. We're just going to reorder everything because it's all multiplication, once again, so I can use the commutative property to do that. So I'm going to write -8 and then times 4. Then I'm going to write times f. And remember, if it's f to the first power. Then we have an f to the third over here. And when we get a whole bunch of terms like this, it's not a bad idea to cross them off as you're writing them down so you don't miss any. Then we're going to have g to the second, and then g to the third, and then h to the third, and h to the sixth, just like that. All right, so we got everything there. Now, what we're going to do is go ahead and combine everything. So -8 times 4 is -32. We have f to the first, f to the third, which becomes f to the fourth. Now we have g to the second times g to the third. Those are going to add and give us g to the fifth power. And then h to the third, h to the sixth. Those add up and become h to the ninth power. So we have -32, f to the fourth, g to the fifth, h to the ninth. And then that is our final answer. So that's what I wanted to cover today. The next video, I will show you how some of those other properties work. Thanks for listening, guys. As always, if you have any questions, feel free to email me. Have a great day.